All right, thanks everybody for joining. Today's talk is going to be from two people, Eli Dart from ESnet and LBNL, and Hans Addleman from Indiana University. Both collaborate together within the EPOC project. And today's talk is going to be talking a little bit about routing. It's going to be network strategy to enable data-intensive science. And the undertitle there is to normalize R&E routing policy when there are way too many choices. So I will turn it over to Hans and Eli to drive and to get going.
Okay. So I guess this is Eli. So I have the first few slides of this talk, and then I'm going to turn it over to Hans. Hans got there first, and so we're using his laptop to drive slides. So go for it, Hans. If you could advance the deck. So this is a rough outline of the talk. I'm going to talk a little bit about sort of a brief introduction to EPOC, although to be frank, Jason and Hans could probably do a better job than me. And so if there's virtual fruit to be thrown, they should feel free to do so and correct any of my mistakes. I'm then going to talk a little bit about the R&E routing architecture from a sort of broad strategic perspective. And then Hans is going to go into some of the details about how BGP policy decisions can be used to affect that routing architecture and what that means actually in the real world when we do this. And then we'll open it up for questions after that. So next slide, please. So EPOC is the Engagement and Performance Operations Center. It's a joint project between Indiana University and ESnet. Many of you will recognize the names of the guilty here. So Jen Schopf is the PI. And then co-PIs are Jason, who is here with us, works for the Science Engagement Group in ESnet, as do I. And Dave Gent at the IU Global NOC is also a PI. And EPOC partners with a bunch of different regional and national players across the NSF funded space and beyond. To do a wide variety of things. It's a really good group of people doing some pretty amazing work, and so this is part of that. So Hans and I are presenting this today as part with our sort of EPOC hats on. So there's several focus areas in EPOC. There's sort of roadside assistance, right, which is helping folks out with tuning or architecture issues. Application deep dives, which are modeled on the idea of learning about what the science needs from the network and using that to drive network design and architecture, and also using that to learn how to improve science collaborations on the other side. So this is a key sort of engagement activity. Then there's a whole bunch of data gathering and telemetry and data synthesis work clustered around NetSage. There's some other things like Science DMZ, as a service or in a box, per Sonar Test Point as a service or in a box, and then training seminars and webinars and meetings and consultations. Modeled after and sort of advanced from the very successful previous. For some reason, I can't.
OIN.
OIN, thank you. I even spoke at a few of them, but that was a really successful effort that Jason led in the community for a number of years. So next one. Okay, so let's get into why we're here and what this talk is about, right? Which is as R&E organizations, what do we need to do to make sure that the data transfers that use our networks consistently achieve high performance? A bunch of us have worked with and talked about and implemented the Science DMZ model at the network edge. right? And so that's a really good story for the network edge, right? What happens at a campus perimeter or a scientific facility perimeter, and how you map the resources at that site onto the wide area network. This talk today is how that collection of networks, right, that R&E network fabric behave, right, and what the emergent behavior is from policy decisions made by individual organizations. And so when we're talking about R&E versus commodity networks, okay, so you look at this slide, right? This is a simplified cartoon, and it's cartoonish enough to be hilarious in its simplicity, right? I mean, obviously there's more cloud providers than Google and Amazon, right? There are tons and tons and tons of ISPs. There are many millions of business enterprises connected to ISPs, right? So if you want a picture of how big the internet actually is, right, go to CADA and get some of their maps, and you can lose yourself for hours chewing through their maps. They've got some amazing stuff there. And it's really cool. This is just a simplified cartoon, the point of which is to illustrate the following. There is a subset of the internet that we call the R&E networking community that is composed of networks built by and for research organizations for research mission purposes. And those networks are connected to each other directly, again, for mission purposes, right? So if you think about what the internet actually is, right, it's a collection of networks, each of which was built for the selfish reasons of the entity that built it, and they're interconnected in ways that increase the value of the network for the organization that built it, right? And the sort of emergent phenomenon that we get from that set of networks being interconnected in those ways is the internet TM, right? And that's all fine and that's all great. It's just that the selfish reasons that for which a lot of people build networks aren't necessarily the same as the selfish reasons for which other people build networks. And what that means then is that different pieces of the internet are better or worse at doing certain things. So the R&E network, and by that I mean this sort of collection of types of entities that are here in the sort of blue shaded clouds, right, that are interconnected to each other, right? Those are built to serve high performance science applications. The green tinged pieces are built for other reasons. They all run the TCP/IP protocol stack, right? They all use BGP to exchange routes. Right? That's all the same, but there's aspects of engineering that make the R&E networks behave differently than the rest of it. So next slide. So as I just said, right, R&E networks are engineered for science traffic. So what does that mean? That means if you have large scale science traffic, right, if you need to sling large scale data sets around, what you really want is the traffic flows that are resultant from those sort of higher level semantic operations. If I want to transfer data set, X from site A to site Z, we want that to stay on R&E networks if possible, because those are the paths that have been engineered to support those large-scale data-intensive science operations, right? They've got the bandwidth for it. We've put in the performance engineering for it, right? We've all got our Personar boxes. We've used them. We've debugged the network. And so what we've got now is a network infrastructure that forms a solid foundation for the type of workloads that we've deployed it for, right? As well we should, right? And that all makes sense. The thing is, it's not just one central entity doing this, right? This is a community of organizations, each of which owns a piece of the puzzle, and we all have to do our part in how we interconnect to each other in order to bring about this emergent behavior that we want, right? Which is that science flows stay on science networks so that the science flows get the advantage of traversing a network that's designed and built and engineered to support their needs, right? So I'm going to go into a couple examples now. If you could turn the next slide. Right, so here, this is something that crossed Jason's and my desk a couple years ago. So this was transfers between a couple of supercomputer centers, right? So this is the Ohio Supercomputer Center in Ohio and the NERSC Supercomputer Center in Berkeley. And the data transfers were slow. And it's like, okay, well, they're trying to debug data transfers and they're slow. And so, you do what you do, right? Is you get a group of your friends together and you try and figure it out. And one of the things that we saw was, okay, well, instead of taking the science network, they're going over commodity. And okay, well, so what does that actually mean? Well, so what's a commodity network designed for, right? A commodity network is designed and built and operated to provide sort of megabit class service to billions of flows, right? It's all your cell phones watching cat videos, your Netflix movies, Gmail, right? All the things. When you get a single host pair that launches a multi-gigabit flow between two IP addresses, right? What does that actually mean, right? In the commodity world, that's a denial of service attack, and they see that regularly, right? And so they're set up to catch and kill those things as quickly as they can in defense of their own infrastructure, and they should do that to defend their infrastructure. In the science world, that's just another data set, right? And in fact, it's not something that should be stopped, right? That's the core mission for which the RNE network infrastructure is designed and built. And so we should enable that, right? And so this difference, Jason grabbed a couple of TCP dumps of what this actually looks like. Okay, this is what this actually looks like. And so you can see on the far left side there, right, it looks like, this is TCP trace output from analyzing a TCP dump file, right? And you see the traffic ramp, right? It's your typical, TCP exponential ramp until it hits the denial of service mitigation stuff. And it just gacks, right? So data transfer just flattens out to nothing, right? And it goes 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 until the thing dies. Right. But so this is, y-axis is TCP sequence numbers. The x-axis is time. And so you can see like starting, what is that? That's like a second and a half, 2 seconds into the flow, throughput stops. And okay, so that's their denial of service machinery functioning as it should. Not so great for a data transfer. Next slide. So this is not the only example of this sort of behavior. So there was something that Géant published. It was a study that several folks did on comparing commodity versus RNE paths, and they saw the same thing. And in fact, they saw two things on the commodity path. One, packet loss, right, which we in this community have talked extensively about as a major performance limiter for TCP-based data transfers, right? But then they also saw the same thing, that you run into the DOS mitigation machinery immediately, and kabang. And so what that means for the scientist using this is that they have to troubleshoot it before they can use it. Right. And if I have to troubleshoot a tool before I can use it, I'm not going to use the tool, even if the tool is a critical enabler for my science. Right? I'm going to find something else to do because there are only so many hours in the day, and I just can't. Right. There's another one of these that was published as well. And this is sort of a multi-nation state test of RNE versus commodity paths. And the RNE paths performed better. And they point out sort of even with more hops, right? There's a key point here, which is that hop count is a legacy performance metric. Okay, there's a lot of us who have been around a long time and remember the bad old days of CPU based routers. I mean, not the routing engine, right? But the actual forwarding was done on general purpose CPUs. Okay, modern routers are ASIC based. Hop count is not a relevant performance metric. Provisioned bandwidth, available bandwidth, and tolerance to burstiness, packet loss, those are relevant performance metrics. Hop count is not a relevant performance metric. And so if you look at there's this common theme here, right? RNE networks are engineered to support the science. Commodity networks are not engineered to support the science. And as I said before, right, this is not particularly surprising right? This is the set of selfish reasons for which each of these classes of network are built and deployed and operated, right? So the commodity folks have a set of things that they need to do and a set of risks that they need to manage. And that includes don't tolerate sudden traffic spikes from IP address pairs. So what does that mean, right? That means we have to keep the science traffic on the science networks as a community. Next slide. So what do we have to do then? So if you think about, routing 101, right? What is routing 101? Announcements attract traffic, right? If I announce you a prefix, I expect to get traffic back from you destined for that prefix. And we have a bunch of routing protocols that are used to exchange that reachability information, and the aggregate emergent behavior of all of those routing announcements and all of those policies determines the path that traffic takes through the network, right? And BGP has a rich policy language for doing those things. Now, BGP is a path vector protocol, right? And the path vector is composed of the autonomous system numbers, right, through which that prefix passed on its way to your box. And because the way BGP works, right, is it prefers a shorter AS path for a given prefix. And if the AS path length is the same for a given prefix, then other criteria come into play, right? This is the BGP path selection algorithm. So remember though, hop count is not a relevant performance metric, and we want to keep traffic on science networks even if the path is longer, right? If the path is longer but has higher bandwidth, that's still going to serve me better. And in fact, if you look at the structure of routing in this case, the RNE path is going to be longer in the general case, especially when two organizations peer with the same commodity provider for commodity transit, right? The RNE path is going to be longer in the general case from a BGP path vector perspective, absent other policy. And so if all we do is stand up a bunch of BGP peerings, let the routes fall into one big kettle of soup and let BGP sort it out with no assistance, we're going to get pathological behavior. So next slide. So this is an illustration of what happens, right? And the Internet 2 ASN is the only ASN on there that's accurate, because all the rest of them could be anybody, right? But if you look so you consider two campuses, right? And each campus has an upstream commodity ISP that they use for commodity things. And then they have a connection to their regional. Their regionals are interconnected by Internet 2, right? That path through the regional and through Internet 2 is 100 gig clean the whole way. And they've got a 10 gig path into this commodity provider. If all you do is dump your prefixes into a common BGP bucket with no policy assistance, you're going to have an AS, so campus 1 is going to hear campus 2's prefixes from the commodity provider and from regional 1 with a much longer prefix or a much longer AS path from regional 1 than through the commodity provider. Excellent, I'm going to choose the commodity provider. So now I take a commodity 10 gig path with all the DOS mitigation mechanisms thereunto appertaining for my science flows. Doesn't work out so good, right? So what we need to do then is harness BGP's policy machinery to deal with that. So I see there's a bunch of discussion and questions coming through here.
I can read them to you if you'd like, Eli.
I got them right here. Okay. So how does one overcome the visceral ingrained primal belief that hop count is important? You repeat this so you're blue in the face. There's no other way. Not that I've found. And I'm sorry that it has to be that way, but unfortunately that is what it is. So Jason's question, referring to users asking about hop count or admins being concerned about hop count. I run into all kinds of people who are concerned about hop count. I run into network administrators, system administrators, users. Everybody has been trained to think that hop count is an issue. And on a 100 gig clean path through ASIC-based routers, hop count is not a reasonable metric. And all we have to do is tell people that. There's no other way. I don't know what to tell you. Tim, I have not seen an example of RNE networks crushing science flows with DOS mitigation, but I don't know for sure that has never happened. So I'm afraid I don't have a clean answer for you there. What if we care about latency? It really depends on the application. If you have a low bandwidth, constant rate, loss tolerant, latency sensitive application, then the commodity path might be good for you. If that is in fact the lower latency path. Because remember, hop count doesn't necessarily determine latency either, right? So if I peer with AT&T for transit, right, in San Francisco, and somebody peers with AT&T for transit in Washington, D.C., there's still 70 milliseconds of round trip time across the United States to deal with that, right? Because, okay, if you can fix speed of light, there's a Nobel Prize for you. And I think you should get on with that, and that's great. Until then, that's the world that we live in. I don't think you're going to see appreciable differences in latency on a cross-country commodity path versus a cross-country RNE path. And so for most of the data transfer applications that we see, clean, plentiful bandwidth is much more important than latency or hop count. So next slide, if you could, Hans.
Whoa, there.
So from a backbone provider's perspective, right? And so I'm going to talk a little bit about how ESnet organizes its routing internally. We make extensive use of BGP's policy knobs to manage exactly this sort of thing. So we have a whole bunch of BGP communities, which are tags that you can assign to routes. We make an extensive set of decisions based on those community tags, and we have a set of local pref tranches for different classes of routes that govern their behavior inside the ESnet backbone. They also control who we announce them to, but that's another set of things that I'm not going to get deep into right now. The main thing, though, is that we make extensive use of BGP's policy knobs internal to the ESnet backbone to ensure that classes of traffic are treated appropriately for performance engineering reasons. And local pref's the big hammer, right? Local pref supersedes AS path length, and it allows us to say, okay, I got this prefix from a science network, and so I'm gonna treat it differently than the prefix that I got from AT&T or Hurricane Electric or whomever. And so that that allows us to do a sane job of managing performance. Now, this is more complicated than you would need as a campus, right? So we're a nation scale backbone provider, and so we have additional complexities that campuses don't. Campuses have additional complexities that we don't. But the idea of using BGP's policy mechanisms, right, to make decisions about how your routing behaves is the key point here. Next slide. So, what I mean is some of what I just said, right? So, what are the goals for a backbone, right? We need to manage BCP38 filters, right? We need to be resilient to routing leaks and other things like that, right? Manage multiple peers. There's a bunch of stuff that shows up in the backbone case that doesn't necessarily show up in the campus case. In the campus case, there's a bunch of stuff that doesn't necessarily show up In the backbone case, I mean, we both need to manage, our transit costs. In some cases, that's different for a campus because, for example, a university campus has dorm rooms. It provides transit for dorm rooms. ESnet does not, for which we are grateful. But another thing that's sort of key is the campus routing policy can support the campus perimeter security policy. And so there's some crossover there between tool chests. There's a common goal that we all share, though, which is science flows should see high performance from the network infrastructure. And we also want to reduce the costs that we have for the networking capabilities that we have to deploy. And so one common example of this is that in many cases, the connection that you get for science networking is flat rate, and your transit is often charged by the bit. Now, these aren't true in all cases in either one of them, but if you have that sort of trade-off, then using BGP's policy mechanisms can save you actually a bunch of money. So the point of this is not to tell people to replicate ESNet's internal routing policy, right, on a campus perimeter, right? It's not necessarily the right thing to do. And as we've said in networking forever, and we'll continue to say forever, know your network, right? You as the network engineer with root on your infrastructure, it is your job to know your network and do what's best for it, right? And even if somebody tells you A, B, and C, and you know X, Y, and Z is correct, do X, Y, and Z, right? It's all you. But if you understand the tools that you have, then you can get the most out of the infrastructure you've got and the network connections that you've got. And included in that is the ability to keep science traffic on science networks, right? And this is something that everybody has to do unless you only have one upstream, right? And your provider's doing that for you, in which case, hey, great. But as soon as you have multiple exits from your campus, right? This is a set of decisions that you need to make. Next slide.
So Eli, I'm going to jump in here because I think there's a relevant question before you get off that one. I'll repeat it. I expect a number of us are routed through a regional network. In our case, it's Merit. Looking at these tools, what sits with the regional and what sits with the campus?
So as Dave just points out, it depends, right? So in every single one of these cases, right, the answer is always it depends. And so if you have a regional that handles all of this for you, it may very well be that the regional is already doing this in a sane way, right? So if the regional is preferring R&E paths for routes that they get from R&E peerings, then to first order, they're doing their part. And you can test this with traceroute, right? I mean, you can see, PerfSonar allows you to do these things, right? There's another pitch for PerfSonar, right? It allows us to see what the path someone else would take back to us is. It doesn't give us the full capabilities of a looking glass, but it allows us to see, okay, if that PerfSonar box traced back towards me, what path would I take? What path would traffic from that box take? And if that PerfSonar host is covered by the same prefix as the DTN cluster that you're trying to get to, right, then to first order, they're likely to behave the same, absent, somebody doing really sort of detailed routing policy for just that DTN cluster or just that PerfSonar host, right? So in many cases, if the regional's already doing this for you, that's great. If you have a campus perimeter where you have to make some of those decisions, then some of those decisions are on you. Presumably, you could ask Merit what their policy is, and they should be able to tell you. Okay. So I am now going to hand this off to Hans, and I'll stick around if there are questions from me at the end. But Hans, it's your bunny.
Thanks, Eli. So over the last couple years, EPOC's been going for almost 2 years now, or a little over 2 years now. We actually have seen in a few actual real roadside assistance cases, as we call them, where this kind of thing would have really helped. Um, so I thought I'd go over a couple of those and then talk about some of the things that Eli kind of touched on, but how we can use that to affect our traffic and our routes. So this one was interesting. So it was this is a case where they actually had multiple connections to a regional provider, and they were doing the right thing. They were choosing the regional. However, the traffic just was coming back an older congested 10 gig link. We made some changes, or the campus engineers, excuse me, made a few changes to their routing policy, and you can see the transfer rates skyrocketed. And in the second example, another routing asymmetry problem. The R&E path was being chosen coming in. They were choosing commercial path out. In this case, the regional, and every regional is different. So, know your network, also know a network engineer, and have a good relationship with someone at your regional that you can work through these issues with, because it is kind of a partnership there, or it definitely is a partnership. But this regional gave they had transit, they had links to ESnet, links to Internet 2, etc. And they would bundle up that whole routing table and hand the routing table directly in one big kind of explosion towards the campus. So that really left the campus at a place where they needed to really make some local decisions about where to take traffic. And after looking at some of their routes and messing with their local press and talking to them about this, we got them moved over. Yeah, I've only got one slide, and fixed. And they're, I don't even remember what kind of science this was, but they had pretty big data sets, and those, of course, took off. But anyways, Eli's been saying this, and BGP really does need care and feeding. And it's, as Jason says, TCP kind of just works. Well, so does BGP, right? BGP, you set it up, you can walk away, you're going to get transfers, things will work, but really, like Eli's been saying for the last half hour, you have to tune it, you have to pay attention to it. Path selection for BGP for every single prefix is quite the thing. In some cases, it's as long as 13 steps. But you can see what Eli was talking about. Local preference is basically the first thing it looks at, right? So local pref is that big hammer, and AS path is, your second hammer. And so I also mentioned, I think, community strings. So these are really powerful. This is where you and other networks and your regional and your national network can provide clues or hints or information about every single prefix that they pass to you. Every prefix can have multiple of these strings. And, honestly, and Eli and I were actually talking about this just yesterday. I think it's important, and sometimes you might have community strings that are internal, and you use internal and you don't need to publish those. But if you are putting community tags on prefixes and advertising them to neighbors, you should probably have a web page somewhere that lists what those mean. Unfortunately, the tag is literally your AS number and some random string that you make up in your policy. So that needs, if you want other people to be able to direct their traffic based on what you're telling them, you need to make that public somewhere. Or, when you bring up a peering, send them an email and say, hey, here are my community strings. Anyways, I think, yeah, so here's Internet 2 actually has a wonderful web page, and they do a lot of different community strings on their prefixes. They let you set your local pref. They'll even tell you, if it's going to a commodity provider, a cloud provider, which cloud provider. They'll tell you around your network where it's going. Is this prefix coming out of New York or LA? That can help you even with your latency, right? You can steer your traffic towards where you think is going to be the shortest path. They even have an emergency prefix. So if you're getting DOSed or something bad is happening, you can say, hey, please stop sending me traffic. And of course, you can pad your ASs. It's really powerful. Most regionals have something like this too. I know the Indiana Gigapop does. Let's see. So just talking real quick about these, local pref is something you set locally and it modifies your outbound, and higher always wins. And this gets kind of crazy because it kind of bounces back and forth between that BGP in that whole path selection. Some things are higher and some things are lower. So you just got to, print that out and stick it next to your monitor. So higher preferred for local pref. And I think, with BGP communities and things like that, you can use your policy to really steer the traffic where you think it needs to go. AS path padding, we talked about, is an AS path the ultimate thing anymore? No, not really. But if someone's not paying attention to your communities or overriding things like that, you can make a route that you advertise to someone not look as juicy as, say, another route or another advertisement. And so then, this very rarely comes into play, but it can, I think it's the fourth or fifth thing in the BGP path selection process before you get to things like, is your router number higher? Anyways, say if you have two connections to a regional and the regional would really like you to use this one, they can advertise a med on a prefix that, and this one is lower. And if you get down to that, your local, you will actually, follow that med and go out that way. And those are really it. The communities I think are most important, and local pref is very important, as Eli said. So with that, I think we'll take questions if there are any.
All right. Well, thank you both for giving that. First question just came in. I'll read them out. Do you have a recommendation or another talk about how the campus network is designed to support science versus commodity? Is the community still building separate R&E networks to move large science data, or building commodity network that will also support large science flows?
Oh, well, that's, I'll let Eli talk about science DMZ.
Okay. To first order, the answer is, in most cases, the science DMZ model is the best methodology we have for dealing with this. If somebody comes up with a better one, the community will jump to that. But for now, the way folks seem to get sort of deterministically good performance out of their network infrastructure is that you put the large scale high speed data assets, you put their network front end in a science DMZ and get that out as close to your perimeter as you can. And that place at your perimeter where you locate that science DMZ is also where your RNA connectivity comes in. And so that gives you a nice clean path out to the science networks from the assets on your campus that need to talk to those things. Now, you can build your entire campus network to support high-speed data flows. And some campuses do that. What it means is that the performance engineering requirements to support high-speed data transfer end up being requirements for your whole campus network. And in some cases, that increases people's cost a lot. And so in a lot of cases, it's more cost-effective or easier operationally to just put the few really big data beasts in a science DMZ and then leave the rest of the enterprise stuff for the enterprise network. So I understand that a lot of folks have research and science scattered all over their campus. You don't have to build a science DMZ to the researcher's desktop. And in fact, I would advise against that, because as soon as you involve somebody's desktop, you end up with all of their personal desktop applications. And in many cases, you need something more sophisticated than ACLs to defend that effectively. So the other side of the science DMZ model is you want to make those high-speed data beasts simple enough on the wire that you can defend them with ACLs. right? And so you have to come at this from both sides. You can't just stand up a network, a fast network, and put a bunch of vulnerable goo in it and expect it to work out, right? It won't. So it's really important to come at this both from the application side and from the network engineering side. And I would say if Woostel needs some consultation help in this, right, that's what EPOC is for, right? And so I would encourage you to reach out. I mean, the email address is right there. Reach out to the EPOC folks, and we'll get a consultation started.
Well, and Eli, you also said something interesting about, you build your science DMZ, you put your big data beasts inside that science DMZ, you don't build it out to your entire campus. The good news here is that most of your researchers, even going through your firewall, your campus firewall, if they have to get to the science DMZ and back, get data in and out, they're going to be within 10 or 15 milliseconds. And honestly, TCP does pretty good at 10 or 15 milliseconds, right? So you're going to get decent performance in that space, I think, in most cases.
So Jim has a question about BBR. So BBR has entirely different performance characteristics with regard to packet loss. On the commodity side, we don't have a lot of control about what gets sent to campus. How should RNE deal with TCP that may be more aggressive than traditional rate protocols like Reno and Friends? So I have high hopes for BBR. It's not quite there yet, but my hope is, okay. So Matt Mathis gave a really nice talk in this brown bag series, probably about a month ago now, something like that, where he talked about BBR v2, and it's going to be a little bit before that gets deployed in sort of production, CentOS type Linux kernels, right? So, and there's still some engineering work to do to make BBR perform well consistently in high performance science environments. But the reality is that, on 5 to 10 year timescales, we're going to have a short queue internet. And that's going to make life even worse for Reno and Friends than it is now. And so I'm hopeful that BBR will grow into itself, and we can eventually transition to that. For now, I think that we're going to have to engineer for coddling TCP as best we can. I don't really know what else we can do in the short term, unfortunately.
All right. Well, while we have a pause here, I have a couple that I jotted down. If anybody else does have further questions, please type them into the chat room. I think mine is more along the lines of what success looks like in this space. So you've noted that there's a lot of these problems out there, and we've identified some. And sometimes people don't realize that this is a problem. But the converse of that is that when you do end up going and fixing routing by itself, that may uncover other problems. So really, what is a systematic way that a campus that doesn't know what they're up against here can go about trying to make things right for their science? Do you sort of have maybe a quick little punch list of things that they should do? It doesn't have to be ordered, but necessarily, what are some things that somebody who wants to go in and investigate and try to fix a bunch of these things should go about doing?
I know I've been talking a lot. Hans, feel free to jump in if you want to, or if I leave something out or whatever. I would say two things. One is that if you're going to do high performance data intensive science work, you're going to need something that looks like a science DMZ eventually. So you might as well get started building that, even if it's a simple trial version to start with. But I'm going to borrow something from the Personar talks, right? Which is you can't fix what you can't find, and you can't find what you can't see. And so the first thing you have to be able to do is to see what is. And in order to see what is, I would deploy a Personar box at your perimeter. And I would set up tests with your regional. I would set up tests with Internet 2. I'd set up tests with ESnet. And I would start, start characterizing what you've got. And once you can see what you have, then you can start taking steps to improve it, if in fact you need to take steps to improve it. I mean, we've run into folks who are like, oh, you better like get some testing up and see, and they set stuff up and it rocks. It's like, well, excellent. You didn't need to fix anything, but at least you know it's good now, right? And so getting something where you have the data to inform your decision making is absolutely critical. But I'll say, if you're going to need to move data around, you're going to want something that looks like a science DMZ one way or the other, even if it's just a fast path to a DTN cluster attached directly to your HPC storage, right? If that's all you need to do, right, that's great. But those would be my first two things, right? Start work on a science DMZ, get Persona deployed and actually use it, and then build from there.
All right. All right, it looks like Hans addressed Michael's comment there. So I think that we are at the end. I'll give another pause here in case anybody else wants to insert any. I'll thank you both again. We'll make sure that the slides and the video get posted. There we go. Tim never lets me down. What guidance do you suggest where the other end of an end-to-end path is a cloud provider, Amazon, etc., or an industrial collaborator? You might get direct peering for cloud, but industrial collaborators might be trickier.
Yeah, so that gets hard. I remember a consult that someone brought me in on where they were trying to get a whole bunch of terabytes of data, right? A bunch of data out of a regulatory body, and because they were going to do a bunch of data analysis on it, and so we were talking about, okay, well, we could transfer it this way or transfer it that way, and then I asked sort of what they had for connectivity, and they were very proud of the 100 meg lag that they had for their entire office building. And at that point, it's like, I'm sorry, you got to ship disks because you are just not going to get there from here otherwise. What I would encourage, however, is if your industry partner is going to be doing significant work with your university or with your laboratory, having the university partner build into the local RNE, or at least a circuit into the local RNE exchange, and establish a presence at that local RNE exchange is something that's potentially really strategically valuable for that industry partner, because that gets them high-speed data connectivity to the science complex, right? And that's also something where the regionals, I think, can provide a really valuable service to the rest of the community, right, is by bringing their industrial partners onto the science network, or at least the R&D labs within those industrial partners. And so that's more strategic, right, than sort of one project. But I think that's really valuable when we can do that. For cloud, Michael correctly points out that Amazon doesn't behave like a normal entity, right? Where you're supposed to announce the same set of prefixes at all pairings from a given AS. Amazon doesn't do that because Amazon is not well connected internally. And you just kind of have to deal with that. But connectivity to cloud providers is another way that a regional can provide significant sort of capability for its connectors. And certainly something that ESnet does for our constituents. Internet 2 also does for their constituents, right? We have high-speed connectivity to major cloud providers in multiple locations. And so, that's something on the networking side, right? Where if we invest in that infrastructure on behalf of our constituents, then when our constituents need cloud connectivity, we have it.
Okay, and another question here from Patrick. campus science DMZ to the perimeter or beyond out to a hub like Chicago?
So I'm going to ask for a little bit of clarification there. So you're talking about how to build from a campus science DMZ out to the campus perimeter, or are you saying like connecting your science DMZ directly to a peering exchange and bypassing your regional? I mean, I think we've seen both of those, but if you want to clarify that a little bit, I can we can try to answer that. And Vass, you're right. I mean, Amazon's trying to do traffic engineering by doing that, and by selectively announcing prefixes, and I think that's because they just don't want to be somebody else's transit network, right? They want to make that not their problem. And what it means is it's an externality, right? And they use routing policy to inflict that externality on the rest of us. For persona architecture, I see. So designing a personar testing architecture is something that requires a little bit of nuance. So if you have a 10 gig perimeter and you put a 10 gig personar box next to that 10 gig perimeter and test to the 10 gig personar box on the other side of that perimeter, you're going to saturate that perimeter, right? And I would not recommend doing that. It's a good way to hurt yourself. And you will actually cause the packet loss that reduces performance. Ask me how I know. I think that this is a longer discussion, which I'd be happy to have when we've got more than 5 minutes to go. But if you can measure a long path and the long path is clean, right, then you don't have to measure the short path that's a component of that long path. And so you can use your perf-sonar testing methodology, right, along with your knowledge of network topology to be efficient in your use of throughput tests. For OAMP latency and loss tests, you can be much more sort of profligate in the way you throw those down, because they're not actually gonna get in anybody's way, right? It's just it's a thin stream of tiny grams. So I think designing a personar test methodology is a larger discussion than I want to get into here, but we can certainly do that. And I'm pretty sure actually, Jason's got a bunch of slide decks from OIN that already talk about that. There's material out there we can point you to. Other questions?
Nope, it looks like everybody just having fun arguing about Amazon, but that's quite normal.
Yes.
All right, so I think that we're at the end here. I'll give it the old 5-second college pause here and wait. Thank you again.
I see a lot in the group chat, people saying, this should be a discussion. I really think it should, right? We should, BGP has become less in vogue, and I would like to, I don't know if I want to bring it back again, but I want to make sure these discussions happen, right? Between the regionals, the national networks, the campuses, I would like to see a birds of the feather session start up again if we ever actually meet in person again. But, anywho, I there's a lot of talk about keeping this discussion going, and I think that's great.
Yeah, Hans, I think you're 100% right. Totally agree. Yep.
And until we all can physically meet again, there are things like mailing lists, but certainly lots of good stuff here. So thank you guys for taking the time. Just a note for everybody who's still listening online here, we're going to have a lot more talks sort of in this area of expertise. We have a couple coming up related to routing security, a couple related to things like manners and RPKI and IPv6 handling and a bunch of other things. So we're going to keep this conversation going, hopefully. But also try to record these and post them in places that you can share with your campuses and your younger engineers as they come up, since a lot of this knowledge may start to go fallow pretty soon. So hopefully this will be good for continuing the conversation. We had a late breaking change. We will not have a talk next week, so we're going to be on a 1-week pause. So we will pick up again on a special date. It's going to be Thursday the 14th, because we're going to have an international speaker across the date line, and he didn't want to get up on Saturday, and I certainly don't blame him for that. So look for the announcement. Thank you again to Eli and Hans, and I hope everybody has a good weekend.
Thanks all.
Thank you.